Our third plenary speaker today is Professor Marek Kowalski. He's coming from DAISY and the University of Humboldt in Berlin. And he's going to now talk about what comes next. We've heard about PeV and AV neutrinos, and Marek is going to talk about a joint view of both of them.
Okay, so thank you very much. So I was asked to sort of project a little bit into the future, as if I know, and then I was also asked to essentially present to you a few conclusions from a recent workshop which we had at Weizmann Institute in Israel at the beginning of the year. And so I'll here and there sort of add some of our conclusions from this workshop. And finally, I will embed everything in where we stand right now. So I will be reviewing just a little bit of IceCube results, and here, and here I'll be wearing my hat as a sort of IceCube collaboration member. Okay, so the first slide you have essentially seen already this morning, and it's actually the argument is old. It's more than it's much more than 20 years old. In fact, it was used, I think, to get IceCube off the ground. And, but it's still true. And I think the new version of the plot looks even better, because if you look at this, what you're seeing is sort of distance, how far you can look with neutrinos. As a function of the energy, you see that the sort of the gamma opaque region in that plot is actually a big chunk of the total spectrum that is accessible through any other means. And so if you look at this, you know, if this is what you're seeing here, so essentially the full spectrum from the radio to the highest energy cosmic rays, and what's dark, what you cannot see with photons, is almost a quarter of the total spectrum. And I think this is a very strong argument for neutrino astronomy as a whole. We want to sort of bring light into this region. And why this plot actually works equally well, or even better perhaps, than 20 years ago, is that we now know that, in fact, due to the observation of IceCube, that it's seeing neutrino events in exactly the right energy regime where the universe is most opaque. That tells us that the idea actually works. We have a messenger that can sort of bring light into the darkness. And so, yeah, this is the event that Francis has shown. This is the highest energy astrophysical neutrino event, or any neutrino event that anyone has seen. Just the energy deposited inside the detector is beyond 2 PeV, and the neutrino energy can be up to 10 PeV or even higher. Okay, so this is sort of the broadest perspective you can perhaps take. But let's zoom in where we stand right now and what we know, because many of the things that the next generation of projects will address actually emerge from what we are seeing right now. So we are not going back to the same questions that we've asked 20 years ago, but actually we have a new set of questions and that we are working on right now with IceCube, and we just have to make sure that the next generation of projects are designed such that they can really deliver the answers to the most pressing questions emerging today. So if you look at the sky map of our neutrinos, and these are not all neutrinos, these are just the neutrinos for which we think the probability that they are of astrophysical origin is larger than 50%. Then you get this kind of sky map, and it's you don't have to analyze it with fancy statistics. You can draw the right conclusions instantly. The first is that there is no obvious cluster, which means we have not detected a point source yet. So that's one conclusion. The second is that the events are distributed pretty uniformly over the sky, which means they cannot be galactic. They must be extragalactic. And so these are already sort of the two conclusions that you can draw instantly with this sky map. But then you can do it a little bit more quantitative, actually, and you don't have to do a lot of math for this. You can ask, you know, what would I expect? Would I expect to see a cluster of events? Would I expect to see a point source? And this is just, ultimately, that's whether you expect something or not is simply a property of our universe. So what we're seeing in this plot is slightly more than 100 neutrino events. So these are through-going neutrino events and starting events combined. And together, let me think, it's a little bit more than 110. I counted them today by hand, actually, this morning. But it's, and so we are seeing sort of from everywhere a bit more than 100 neutrino events. And so what's the chance that, we see more than one from an individual source? And so for this, actually, you just have to compare the expectation from the brightest point source in your sample to the combination of all neutrinos from all sources. And so this is given here. Ultimately, it's the number of events that you expect from the brightest source is roughly 1 over 100 times the number of events that you expect from all sources. And this is equivalent to this, to the solution of Olber's paradox. So there is one sort of one parameter in here, which is of this is due to astrophysics. The sources have a characteristic density, and this translates into a characteristic distance. And ultimately, this, what you see here is that this whole thing scales with the density to the power of minus 1/3, which takes care of the source, the flux per source, and corrects for the appropriate distance. Okay, so if you now say that we have about 100 neutrinos on this side, and this prefactor is 10 to minus 2 in front, then that means you can only, your nearest source will have about 1 neutrino event. And so clearly that's not enough to actually identify that, and that's maybe exactly what we're seeing here. And so what we're sensitive to is a source density at the level of 10 to minus 7 per cubic megaparsecs. And in fact, that is our sensitivity of the project right now. So if you look at what the source constraints actually are right now, then Francis has already talked about this. We're pretty sure that the IceCube neutrinos are not from blazars, at least not predominantly. Maybe 10% are from blazars, but not all of them. They're not from GRBs. Here we are very confident. At most, 1% of the total flux is from GRBs. And the reason why we can say that is we are doing a cross-correlation analysis. We haven't seen anything. But the truth is these objects are rare. And because they are rare, n to the power of minus 1/3 is a large number compared to the more frequent objects. And so we are more sensitive to these objects simply because they're on average a bit brighter. Okay. Now, these are just 2 source classes. These are the rare ones, the brighter ones, and so we rule them out first. And of course, there are many other source classes. And you can go through essentially all the reasonable candidates, and you want to be sensitive in the future, ideally with IceCube already, but this we don't have under control. With the future detector, you want to be sensitive to all of them. And what you need, and this is a sort of a benchmark sensitivity that we have worked on at the Weizmann workshop, is you need a flux sensitivity at the level of 10 to minus 13 times e to minus 2 in these conventional units, TeV per centimeter squared and second. And this will, as I will show you later, will allow to probe all source classes that you can think of. Okay, coming to the diffuse flux, and so there are some questions that are emerging too, and Francis did an excellent job, of course, to already review some of these, so I will just refresh this very quickly. So what you're seeing here, in a sense, is the multi-messenger picture of that is emerging right now. So here you see the diffuse flux from gamma rays as observed with Fermi. This is the cosmic ray flux known since decades and being measured better and better and to higher energies. And here, these are neutrinos. And I should say, this is from an old publication from 2015. I really encourage you to, if you want to see the new data, we have essentially half a session talking about the new data that came out just this year, and some even only at this conference, that is going to be presented later on this afternoon. So go to this session. But in any case, there are a few things that are worthwhile to mention. First of all, you see immediately that the energy budget or the power in neutrinos corresponds roughly to the power in gamma rays and the power in cosmic rays. So that's one thing. But when you do a more detailed comparison, and Francis sort of made the argument this morning already, and if you allow for the possibility that what we are seeing in IceCube is really a steep spectrum at low energies, then this is becoming very interesting. Because it means that ultimately there's more power in neutrinos than there is power in gamma rays. And the only way to achieve this is through hiding the gamma rays. And that means we are seeing gamma ray dark sources. That would be, of course, great, because neutrinos, in a sense, they're made for exactly this. They're made to see those things that cannot be seen otherwise. And so the low energy part of the spectrum is something to watch. And I think it's more than just a data point, as you will see this afternoon. It's really the data, in a sense, if you look at, we have not combined it yet, but if you look at the individual analysis, it does have this feeling that there is something going on. At high energies, there's something else going on, namely that the spectrum seems to be fairly hard, e to minus 2.1, e to minus 2.2. And so this gives us another actually interesting angle, and that could be very disconnected. What we might be seeing are really two populations, one sort of steeply falling and one flattening. And what this could be, it could be this could actually directly extrapolate to the highest energy cosmic rays. And so perhaps it's really not a coincidence that we are seeing the same power that we see in neutrinos as in cosmic rays, but really what we are seeing are the same sources producing the same kind of events, but just neutrinos and cosmic rays. And if that's the case, then the neutrinos which we are seeing here should be ultimately connected to the sources of the cosmic rays. And the data, in a sense, gives us already an indication that that might be the case. But ultimately, we need to understand this spectrum much better than we do right now. What about neutrino events themselves? Can we say something about the flavor? And in particular, is the flavor ratio consistent with the expectation? Francis showed this plot. It's actually, there's a very solid prediction. Astrophysical neutrinos should follow 1 to 1 to 1. And well, this is the sort of the latest plot we've shown at the ICRC. And this is including now, it's done only for the HESE data set. So it's not including all the neutrino events that we have. But what's new is that we have now added a tau neutrino identification method, a new one, which is more powerful and which can ultimately detect tau neutrinos down to a few hundred TeV threshold. And so we were expecting to see about 2 tau neutrinos in our sample. We have seen 0. That is, that's not a big deal. It has a p-value of 10%. We are seeing most likely an underfluctuation, but it's still interesting. And I think it sort of motivates us just further to push further and try to understand, does the flavor ratio really make sense? If at the moment it sort of makes sense, but we need to know much better. And I will tell you about, why this is interesting during, during the later part of the talk. All right, stepping back a little bit further now, stepping back and looking at the whole thing and asking what are the main questions that we have. So I've shown you just what IceCube is observing, what makes us scratch our heads, and ultimately let's see sort of how it comes together. And so this is just a list of sort of big questions that we can ask ourselves as neutrino astronomers. So the first one I think is obvious. We want to actually resolve the sources of IceCube neutrinos. And I've told you already what the sensitivity of the experiment needs to be. By doing this, we might actually be identifying the sources of the highest energy cosmic rays, just sort of as an extra bonus. And so these are 2 independent questions, but they might actually have the same answer. Okay, then there are many other questions. I don't want to go through them in all detail, but perhaps just mention that, as Francis was saying, we might be seeing neutrinos in coincidence with supernova. And again, that would be a poster child for neutrino astronomy. We can look with neutrinos deeper into a star than you can do with any other measure. And then we can explore the universe where it was most active at the very high redshifts, which is otherwise inaccessible, and so on. Finally, I will touch on beyond standard model physics. There's plenty of beyond standard model physics in what we can do in the future. And the projects that we sort of are currently working on, they are actually summarized in this box here. So this is radio, optical Cherenkov telescopes in ice and water, and Pierre Auger. But there are a number of activities actually ramping up now that are going sort of in all directions. And Markus Ackermann, I think, did a nice job in summarizing them in this chart here. So there is the precision frontier, which is essentially trying to do what we are doing with IceCube, but just slightly improved and at a different site, for instance, to get a complementary view in the north, but also adding, for instance, better resolution, and that would become 3net. And there is, this is the precision frontier, there is the intensity frontier to simply accumulate more statistics. I mean, in almost everything we look at, we are statistics limited, and so we just need a bigger detector, and this has to be an economic solution, and so we are proposing IceCube Gen 2. This is the intensity frontier. And finally, you want to push to the highest energies, and Abby gave a nice talk just before the break, and so that the energy frontier can be easily, best perhaps assessed with radio. So just 2 slides on the various projects. So CAME3Net, it's a project just like IceCube, but at a different site with different technology. They have done a great job to develop the technology specific to their purpose. So these are these sensors with not just one PMT, but many PMTs, 31 small PMTs look in all directions. They are going to be deployed on strings, many more than IceCube. So it's 115 strings per block. And the CAME3Net comes in sort of in 2 different configurations, ARCA and ORCA, which will be built simultaneously. ARCA will consist of 2 blocks, looking like this, and ORCA, a dense array, sort of to measure neutrino oscillations, will be 1 block, just much denser instrumented. And ARCA will be built in Italy and ORCA in France. And so this project is already under construction, and what you're seeing here is the anticipated angular resolution for muons and for cascades. And this is one of the strengths of this project. We'll have a better angular resolution if everything goes according to plan than IceCube, and it will be a different site. So it is a complementary project, and I think it's going to be very useful for that. All right, there's a smaller project going on at Baikal, which is nevertheless worth mentioning because it's simply evolving pretty well. They're constructing, and even though the goal is only to build a 0.4 cubic kilometer array, they are on track. They have 2 clusters out of 8 already in the ice, and within 3 years they have a chance to be completed. And so the goal would be then to have a 0.4 cubic kilometer array that's the GVD. Finally, there is, a little bit further in the future, there is IceCube Gen 2, and you've seen this already before. So it consists of many components, and it's actually it's an observatory or a facility that can provide sensitivity over a very large range in energy, from MEV to EEV neutrinos, and it's doing so by employing different technology. So it's foreseen to have a surface array, a very large in-ice array, which will be an instrumented volume, a factor of 10 times larger than that of IceCube. But it will not cost a factor of 10 times more, but only maybe 50% more than IceCube. Actually, not even that. We can perhaps, with smarter technology, do it for the same price. And then there will be a very dense inner core, and we are now actually developing the case for a radio array. And I'll just jump sort of to the performance. So here you see this point source sensitivity, and as a function of the declination. And I don't want to go into the details how to derive these, but we will be able to see, look for point sources from the south as well as from the north, with variable sensitivity and variable energy range. But one of the most important aspects is that we're going to touch the sensitivity that we need to actually be able to see all the sources. And you can, I've mentioned that this at the beginning, but now I want to sort of give a little bit meat to the argument. So what you can do is you can take all your source classes, all your candidate sources, and you can arrange them according to density. And then you can ask, imagine that a source class actually is responsible for the IceCube diffuse neutrino flux. Would we be able to see it or not? And so if you take a source class, let's just take this subclass of BLX, and you want to saturate the IceCube diffuse neutrino flux, then you know what the luminosity per source is. And this can be then tested through comparing it to the point source sensitivity. And if it's above the green line, then we have sensitivity to this source class, at least if it's responsible for the neutrino flux observed by IceCube. And with IceCube Gen 2 sensitivity as projected, we will be having a sensitivity essentially to all the prospective source classes. And so this is in a sense our goal, and already with current technology, we think we can achieve it. We're working to even improve the sensitivity by using newer technology, but already now we are confident that the scale would be appropriate. In terms of the diffuse flux, I mentioned at the beginning, there's lots of interesting things going on in the spectrum, at low energies as well as at high energies. This is how the situation could look like with 15 years of IceCube Gen 2. So here you see essentially what we have assumed here is a spectrum, and this is a pure Monte Carlo result, of course, a spectrum that first follows like e to minus 2.5 and then becomes flatter, like e to minus 2. And so we are having two components, superposition of essentially two population of sources. And what you're seeing is here is the expected error bars, and the small numbers on top are just the event numbers per bin. And what you're seeing is that we will have very small error bars, and so we can do very detailed measurements of the spectrum. But what you also see is that the event rates are actually large, and they're large up to 10 to the 17 electron volts. 10 to the 18, we'll be finding events above 10 to the 18 electron volts if the spectrum is indeed as hard as we think, or as it could be. And that means that we'll be doing not just neutrino astronomy, but we can actually do physics with these neutrino events themselves. Each neutrino, for each neutrino, ultimately you can estimate the cross-section, for instance. Okay, so this is this spectrum, and what you see also is that we will be able to connect to the highest energy cosmic rays, in particular because if the sources are really the same, highest energy cosmic rays and neutrinos, the neutrinos will come out of the source at lower energies because they first have to interact, and then the pions and have to decay before you have the neutrinos. And so, an energy of 10 to the 8, for instance, here corresponds to something beyond 10 to the 9, almost 10 to the 10 in terms of cosmic ray energy. And so if we can see this kind of spectrum, then we are certain that whatever we're seeing in neutrinos is really connected to the highest energy cosmic rays. Okay, so this is how the picture could look like with Gen 2. I have, just to give you a sense of the beyond standard model physics, I'm also presenting you here a result of a new work which was done with a PhD student at DESY and Walter Winter at DESY. And so what you're seeing here is the Gen 2 contours, the expected Gen 2 constraints on the flavor triangle that we will be able to achieve. And what you're seeing now in this, in the colors here is essentially the phase space by beyond standard model physics that, essentially, how beyond standard model physics shifts the expectation in the flavor ratio from 1 to 1 to 1 to any other ratio. And you're seeing that the whole area here is covered. So that you'll essentially find for every point on that plane, you'll find one BSM model that will be able to shift from here to here. And there are a lot of different models, of course, that you can employ. But what's interesting to see, and what we have done, is we have actually quantified what the parameter space is that you can constrain. And it's pretty, the jump is pretty striking. So for instance, if you compare to IceCube, for instance, I don't know, let's take, effective sterile neutrinos, for instance. Right now, IceCube can only say something for 10%, or exclude only 10% of the parameter space, while IceCube Gen 2 will be able to see 86%, so almost all of the parameter space. So this is just showing you the strength of this new data that would be coming up. All right, so the last few minutes I have on different kind of experiments, but I don't need to go into detail because we've just seen a great summary. So this slide you have seen already before in Abby's talk. The one thing I would want to say is there are all these missions which are being developed right now. Each of them have something, I think, strong going for them. The interesting aspect, and this is also a result from the Weizmann workshop which we had, is that the collaborations are talking with each other and thinking whether they can actually merge their ambitions and build a super sort of radio detector. And there is discussion between ARA and Ariana to actually build a combined detector at the South Pole. And that actually, I think, is needed because ultimately, if you look at this plane, the flux versus the energy, you do want to touch in a sense, the lowest predictions. And what we have at Weizmann, what we came up with is that sort of as a benchmark, as a target flux, is 10 to the minus 9 times e to the power of e to the power of 2 in GV, centimeters squared, and so on. So the conventional units. So this is our benchmark point that sort of the next generation radio observatories should reach, should target, to do, to make sure that there's compelling science to be done. Okay, so this is my next to last slide. So this is just a timeline of how this can all evolve, and because this is a little bit, this is our timeline. I can just say, read it, but of course we all know that it can slip. We are working on making it possible. But I don't want to go through the detailed timelines, but rather I want to go through some milestones. I hope in 2022 that KM3net will deliver the first northern cubic kilometer neutrino detector. And so then we have a complementary view. And I think that is very much needed. It's not needed to prove that we really see astrophysical neutrinos. As Francis, I'm convinced we are seeing astrophysical neutrinos. It's really in the details. We are asking ourselves so many little questions that it would be very important to have a second experiment to back us up. But there's something else in 2022, hopefully. Namely, we have submitted a proposal called IceCube Gentoo Phase 1. And this is a Pathfinder proposal, Pathfinder mission for Gentoo, and we submitted it to NSF, and we have gotten quite favorable reviews, but we're still in the process. But it's not just a Pathfinder mission for Gentoo, it's actually, there's another very exciting aspect to this, namely we are deploying with it new instrumentation and new calibration sources. And these calibration sources are desperately needed for IceCube because they will allow us to calibrate IceCube at a much different level. And once we have deployed these calibration sources, all our methods will work much better. We will get better reconstruction, better angular reconstruction, better neutrino flavor identification. Everything will improve. And the neat thing is, once we have it in the ice, we have 12 years, if everything goes according to plan, 12 years of IceCube data in the box. The detector is remarkably stable, and so we then have to just gain our understanding about the ice, the calibration, and then we instantly have 12 years of IceCube data that is worth, I don't know, maybe 30% more in terms of significance. And so this is something to look forward to, and we just have to now get this IceCube IceCube Gentoo Phase 1 off the ground. Well, maybe we should call it also IceCube Phase 2. It would be equally fitting. But anyway, that's the current name. All right, then the other milestone is maybe around 2030. IceCube Gentoo will be completed, and that is when we will get a big boost in event rates. Event rates will go up by a factor of 10. So we will be, and I think it's necessary because by that time IceCube will be 20 years old. And you're not going to double your event sample that quickly at that time anymore. And so we need a bigger detector that it essentially integrates 10 times faster. Okay, so that's the sort of timeline. And this is just the conclusion. I'm a little bit late with it, so I'm skipping over the conclusion. I'm just jumping to my last slide, which is an announcement. If you like TeVPA, and obviously all of you do, then join us in Berlin next year. So thank you.
Thank you, Marek. We have time for one quick question. Again, raise your hand. I don't see any raised hand. Oh, I see one, but okay, down there. Cool.
Can you just say something quickly about the role of angular resolution at this next phase? You talked a lot about getting down to a certain flux sensitivity. Will the new instruments have any better angular resolution or pointing, and will that be, how important is that going to be?
Yes, it's important, and I mean, it does, well, one should say it's important for identifying the sources of the neutrinos, and it's for measuring this spectrum, for instance, it has almost no relevance. But of course, you know, but for identifying the sources, it is important, and it's we have parameterized the effect, so the sensitivity scales roughly with the point source resolution to the power of 0.6. Yes, and so it's now the new projects will have a better resolution. KM3net will have a better resolution because the water is simply very transparent, and so you don't have to bother about with scattering. Gentoo will have a different advantage. Even though it's a sparse detector, you would think it's actually would have worse resolution, but that's not true. What helps us is that it's such a large detector that we will have a long lever arm. So if a muon goes through the detector, the track inside the detector can be 3 kilometers long. And so that helps us in reducing the angular resolution, improving the angular resolution, and we think we can go down to also 0.1, 0.2 degrees. And we have not yet made full use of the new technology that we want to deploy, so this needs to be properly reconstructed, simulated, and we're working on this, but we are confident that we can push to the level where KM3net is.
Thank Marek again.